All right, so we're going to start out with 6.8 questions today, and we got 27 and 37. I do just want to caveat these questions are a little less likely to show up on an exam just because of the format of the question. Since we're a little bit limited in terms of our technology and the depth at which we'll go into like calculator type of problems like this, just less likely to show up on an exam, but we can still kind of talk to the high level points that I would be interested in you guys kind of knowing for this material. So for 27 here, we're estimating the coordinates of each turning point, and we're stating whether each corresponds to a local min or a local max, and then we're just going to list all the real zeros and determine the least degree that the function can have. So the first thing I want to notice about this thing is it's opening down and it's opening down. So as I see it's down and down, I know that this is going to be an even degree, and I know it has a negative leading coefficient. Now, it doesn't ask us for the negative leading coefficient, but I just like to include that information here as well. So when I'm looking at this problem, I'm seeing I come up to a point like this, and then I come back down. So when I come up and then down like this, that is a local max. And I see I come down to a point like this where it dips and then goes back up. And it's a little bit hard to see here, but I have a local minimum. Oops. There we go. And then over here, I have another local maximum. So in this problem, in terms of turning points, I have 3 turning points. I have 1, 2, 3. So if I look at this thing, I know of least degree, if there are 3 unique turning points, then I'm going to have at least n minus 1 of the turning points is going to be n degree. So as I look at this, I must be at least a 4th degree. And that 4th degree matches up pretty nicely with the fact that we know it's got to be even negative. So here we find a local max, and a local min. We can approximate these points. So this looks like -2, 1. And again, just approximations for these is really all I care about. This looks like a local min at 0, -2. And then it looks like I have a number, I'm going to call that 1, -2. Oops. So here we have our 3 turning points, each labeled right here for us. For real zeros for this thing, I don't have any points that cross my x-axis. So I don't have any real zeros here. So I'll say there are no real zeros. What that means is I'm going to have some imaginary ones. So again, this thing does not actually cross my x-axis, so I don't have any actual real zeros. Just to point out a couple real zeros here for you, if we're looking at 23, here's a real zero, there's a real zero, there's a real zero. Looking at 24, real zero where it touches here, real zero where it touches here. So just some examples of real zeros, but this problem number 27 does not have any. So we estimated our coordinates, we found the local mins and maxes, listed all the real zeros, and determined the least degree. We said the least degree must be at least a 4th degree. Could it be 6? Could it be 8? Could it be 10? Sure, but it's at least a 4th degree because I have 3 turning points. Any questions here? Perfect. Let's look at 37 next here. So we're given some information about these dwellings. I guess it would be kind of cool to include a picture with it. So basically looking really at these kind of like super model efficient homes after the war, just trying to create space for cheap. And we're given a model which is that the surface area is equal to pi r squared plus pi rl. So if we think of the surface area for a cylinder, this is kind of what this is coming from. And it's just saying, okay, well, instead of having 2 of the pi r squareds, I'm only going to have 1 because I have half at the front of my house and half at the back of my house. And then instead of this being 2 pi rl, again, I've only got half of my cylinder. So that's where this is coming from in terms of like, hopefully we've got some geometry roots that we remember some of that information. So here we're given this formula and we suppose that we have 600 square feet of material to build this. So I'm going to basically just say 600 is equal to, and now I'm just going to go pi r squared plus pi rl. And so here, formula is given here, radius of the semicircle and L is length of the hut. Substitute 600 and solve for L. Okay, so we can solve for L here. We're going to have it in terms of a variable R, but that's okay. So when I'm looking at L here, this is not my best R. There we go. So when I'm looking at trying to get L by itself, I just want to first get all of the other constants away. Now I don't know what R is, but it's just a constant here. So I basically want to start by subtracting pi r squared from both sides. Sorry, my R values are barely legible at best. So I get 600 minus pi r squared, and that equals pi r L. So again, wanting to get this thing by itself, what am I going to do? So my next step is to then divide. So I'm going to divide by pi r. I'm going to divide by pi r. So in terms of what I would be looking for an answer, this is the point that I would stop. If you want to simplify and like split these things out, you could, but I would take this as a final answer and that'd be fine. So my L value equals 600 minus pi r squared all over pi r. So if I wanted like an actual example of, the dimensions for this size of hut, then I could basically say, okay, well, what if my radius was, and then we just, make one up. So I don't know, maybe like, looks like 5 or 6 feet. So again, this is not part of the problem. This is just totally to relate like how we're going to talk about this thing. So the bigger I make my radius, basically the shorter my house is going to be, the length of the house, because the more area I'm using here and the more area that's got to be used around, the less material I'll have to run the length. So just as an example, if you want to plug 5 into this thing, so if we're doing like r equals 5, we would get something like 600 minus, I'm just doing this on a calculator. There's no way I would expect you guys like to, be doing this stuff out. So minus 25 pi, and then we divide that all by 25 pi. So this seems to give us a length of approximately 6.64. So we can kind of see like why maybe they would call it a hut here, or maybe just 600 square feet is not a reasonable estimate for the amount of material it would take. So I don't know. I mean, I kind of imagine like this is like a 2-foot door. So if I cut half the door here, it looks like maybe I have 2 more doors worth for my radius. And that's how I'm just estimating this 5 feet. Again, just a fun number I'm plugging in. And again, this is just an arbitrary limitation on the amount of material. So just kind of like showing you an application of like where this is coming into play. Any questions here?
Where did you get the r equals 5 from?
I totally made it up.
Oh.
Just as an example to show you like what application this has.
Oh, okay.
Totally made up here. Just FYI. Just for fun. Any other questions on 6.8 stuff? Perfect. Call that a wrap.